I'm going to tell you about neuromorphic computing, and I use a lot of machine learning terms in this talk, like backpropagation and training a neural network. But it's not another neural network talk. I'm actually discussing spiking neural networks, which are a lot more complex systems. So right now, your brain, running on the power of whatever you had for breakfast, is doing visual processing, recognizing what it's seeing, facial recognition, speech recognition, balancing you in your chair, and more all at once. If your computer tried to do all of the calculations for all those tasks, it would melt. So could we design computers to work like the brain so they're more energy efficient and faster? Well, the answer is no, if we stick to digital computing. Neuromorphic computing is a completely different kind of processing that might allow for this. And these neuromorphic computers aren't just fantasy. The Intel Loihi chip, for instance, runs on around 1/10 of a watt, while your computer right now, for reference, is running around 100. That's 1,000 times energy difference, and this technology is just beginning. Here's the catch. You can't program them like a normal computer. You can't use a language or algorithm to tell it what to do. So how do we use them? And my hypothesis or proposed solution is like this. Because these systems are meant to work like the brain, we have to treat them like the brain. We have to teach them rather than programming them. So to test this, I trained a neuromorphic computer to replicate a model of the brain's visual perception. So your visual system uses only time series spike signals. That is, whenever I say spike, I mean a discrete pulse of voltage. And that travels down your neurons from your eye to your brain. So when your eye sees a cat, its neurons fire a series of spikes to your brain, and then your brain's neurons fire spikes to each other to process this, and a lot of spikes end up in the cat neuron, so you know it's a cat. So our neuromorphic replication of this should only use time series spike signals as well, even down to the eye, which means we first need a camera that sends time series spike signals rather than pixel intensities. That special camera is called the silicon retina, and it works by firing a spike when a pixel changes. And notice, that means if no pixel is changing, if nothing's moving in the scene, nothing comes out and you don't get anything. So it can output both positive and negative spikes. So for example, in this visualization where I move a 5 around, you get these blue and red pixels representing positive spikes where a pixel increased and negative spikes where a pixel decreased. So, and remember, I have to move that 5 around because if I'm not moving it, nothing changes, so you get just pure blackness out. Now, to make these silicon retina visualizations a little easier to understand, I pre-process them so you can actually see what the camera is seeing. So now on the right, you can actually see that 5 that I'm moving around in front of the camera. But remember, the data doesn't actually look like this. This is pre-processed. The real data looks more like this on the left, with very spiky and sparse and difficult to understand. So under the hood, a neuromorphic computer is built like a silicon reconstruction of the brain. That is a vast array of spiking neurons and that stimulate each other by sending spikes down synapse transmission lines. So in that way, it can be described as a spiking neural network. But despite the name, don't confuse this with an artificial neural network, which is what people typically mean when they say neural network. An artificial neural network runs on a clocked digital computer. It calculates digital values one layer at a time. That means later layers are all waiting on earlier layers to finish. And that's also inefficient because of the use of constant voltage values. And each neuron does its job exactly once. It sums up its inputs and creates an output once in the use of the network. Think of how many clock cycles have to run for every single use of the artificial neural network. So much wasted time and waiting around on other neurons. But in a spiking neural network, all the layers are running at once. Neurons are receiving and emitting spike signals continuously in real time without waiting on others. Each neuron is continuously operating for the duration of the network's use, and there are only spikes, no digital values. So the neuron model in your brain, and therefore also in neuromorphic computers, is called a leaky integrate and fire neuron model. Whereas artificial neural networks use a neuron model that computes one summation and that's it, a leaky integrate and fire neuron actually evolves through time and is driven by a differential equation. It has an internal value called its membrane potential. So let's watch the neuron work in an example system with neurons A, B, and going into C. On top, on this top plot, we have the spike trains of neurons A and B, where the x-axis is time. And on this graph is the membrane potential of neuron C. And on the bottom plot is the spike train output of neuron C. So in the leaky integrate and fire neuron, first it leaks, meaning this membrane potential goes down. We see the graph slowly decreasing. Then it integrates. So whenever it receives a spike, it cumulatively sums it up. So the membrane potential jumps up when it receives a spike from either A or B. And then it fires. Once the membrane potential crosses a certain threshold, it resets to 0, and the neuron emits a spike. And there's also sometimes a fourth mechanic to the leaky integrate and fire neuron model. After spiking, it can't immediately spike again for a certain duration of time. That's called the refractory period. And once that time is up, it starts charging up and spiking again. So with these simple mechanics, the neuron works like a simple capacitor. It charges up when it receives a voltage spike. So the leaking can be implemented with just a resistor to the ground leaking off the capacitor. And the threshold is just an air gap or hysteresis diode releasing all of the charge in a spike when the voltage is high enough. A neuron is just these three basic circuit elements, a resistor, capacitor, and threshold. And although the refractory period does add a bit more complication to the circuit, but the important thing is there's no clocks, and there's no fetching from an offsite memory, there's no transistors. In a normal computer, you would have to do all sorts of gates waiting on others to finish, and even just to do a calculation, all sorts of transistors have to toggle to fetch something from memory, and all that has to happen, there has to be tons of clock cycles. But in this, everything happens as fast as a spike can travel down a wire, which is pretty much the speed of light. This is why the brain is so much more efficient. So I don't have a neuromorphic computer in actual hardware, so instead, I programmed a simulation of one on a regular computer, which is sort of ironic since the whole point of neuromorphic computers is to make more efficient computers, but using a regular computer just completely circumvents that. But that means I actually have to integrate the millions of driven differential equations for every neuron and evaluate it and train it. By the way, these simple mechanics of a neuron lead to an interesting response, the logistic function. So if we imagine a neuron is getting spikes at a low rate, that leaking of potential happens faster than it's getting spikes, so it never accumulates enough charge to cross the threshold, so it never spikes. The spiking output rate is 0. When it's getting a lot of spikes, infinitely many spikes per second, the refractory period puts an upper limit on the output spike rate it can produce. And so in between, we have this transition, linear transition, so we get this sigmoid. And this is actually why artificial neural networks use this sigmoid internally. They're just trying to roughly approximate this response of spiking neural networks. So how do we actually teach a spiking neural network system? Although I've said many times how you should not think of a spiking neural network like an artificial neural network, as a starting place, let's think about how an artificial neural network would be trained. In artificial neural networks, one just backpropagates error when it makes a mistake to improve it. But this is a continuous system simulated through time and has spikes which are non-differentiable. So to do this, I'm not just backpropagating error through layers like in an artificial neural network, but through many time steps of the thousands of differential equations simulating the neurons, and through the spike signals. I just so happened to work on a project last year where I also used backpropagation through differential equation integrators, although in the reverse way I'm using it here. And that's what made me especially prepared for this. So we need two tricks to make this work. First, we assign error to spikes that come earlier, an incorrect spike, because those spikes led up to that incorrect spike and partially caused it. And second, to backpropagate through the discontinuous spikes, I use a probability distribution for the chance of a neuron spiking rather than the derivative itself, which would be non-differentiable. So now we have both the things we need to train a spiking neural network, the eye in the form of the silicon retina and the brain in the form of a neuromorphic computer, a spiking neural network. So I trained it for two tasks. First, I wanted a spiking neural network shown handwritten digits to recognize what digit it's seeing with the silicon retina. So you've probably heard of this. This is a very common artificial neural network task, but again, it's using silicon retina data, which yet again is not as clear as it's shown here. It's very spiky and sparse. And it's a spiking neural network, which is a much more difficult thing to train. I'm simulating millions of differential equations. And everything is in spikes. And the second task I want to do is train a spiking neural network to stabilize and integrate from this silicon retina data to an image that we can actually use, because the silicon retina data is pre-processed, so this isn't trivial, and it still has to stabilize it. So to do all this, I programmed thousands of lines of code in Python to create and train and simulate spiking neural networks and to display and visualize data. I created models, found and resolved bugs, analyzed and improved results, and I run my code on the graphics card for higher performance, and it uses stochastic gradient descent. So this takes usually a few hours to train. I'm using libraries like Matplotlib, NumPy, PyTorch, things like that for visualizing data and doing the linear algebra and things of a neural network. And but remember, it's not just optimizing a network, but it's many times over solving millions of differential equations and then backpropagating through that integration of the differential equations to train it. So as an independent variable, you can think of how I tested multiple architectures of the network with varying capacities and kernel sizes and depths. And as a dependent variable, I measured the training and testing loss and accuracy. And all this code is on the GitHub repository. Here are a bunch of photos from my lab notebook to show you the process I went through making this, including plots I made and writing, analyzing them. So what this shows is how I went through iterations of models, displaying results, analyzing them, thinking about how to improve it, thinking about the issues with the model, and repeating until I had a very optimized model. So to measure how well the classifier was performing, I divided how many digits it correctly classified by the total number to get accuracy. Sometimes a machine learning model will memorize the correct answers for the specific examples you train it with. So to combat this, I split the data into training and testing set. And the testing set, I never show it. I hold out until after it's done training. And then I evaluate it to see what it learned. So on this plot here in the top left, we are looking at the accuracy over time, where x-axis is training time. So the blue and orange lines at first go up together, but then the orange line breaks off and levels off lower than the blue line. The blue line goes to almost 1.0. So in this, the blue line is the training accuracy, and the orange line is the testing accuracy. So what this is saying is the training accuracy keeps on going until it's reached almost perfect accuracy, 100%. The testing accuracy levels off way lower at like 60, 70%, which is a problem, which means it's memorizing because it can't actually generalize what it's learned. So I used two tactics to better the model and stop it from overfitting. First, I got a larger data set, and second, I dumb the model down. I take away neurons, decrease its capacity so it has less room in its head to memorize. These both force it to learn the general rules rather than memorize specific features, since the rules are less to memorize than every single example. So this was a sort of engineering project. I went through many iterations of different models and architectures, and I analyzed results and corrected for problems like overfitting. I eventually went too far, to the point the training and testing accuracy were both very low, so I increased the capacity again to get the optimal performance. As you can see in these plots in the bottom right, the accuracy is much higher. The orange line is the old accuracy, and the blue line is the new one. There's a significant improvement here. So the final architectures I came up with were these spiking tensor convolutional networks. This is just to give you a sense of the scale of the networks I made. The classifier, with 3 convolutional layers and 1 fully connected layer, has 289,000 connections in the first convolutional layer. But this is actually only 250 parameters due to convolutional wait time, and the other layers are similar in size. The reconstructor has 4 convolutional layers and no fully connected layer, since its output was an image and not a scalar. So I didn't have a silicon retina in hardware to do this myself, so I got the data from a publicly available data set where an image is physically moved around in front of the silicon retina. And in this visualization of the data, you can see the 5 disappears from time to time, and that's when it stops moving. So it moves in 3 separate motions and stops in between, and that's when it disappears. Like I mentioned, the silicon retina doesn't produce any output when nothing's changing. So back to my 2 tasks. My first task is to classify handwritten digits from silicon retina data. After a lot of training and coding and tweaking and analyzing, I got a model that got it right 95% of the time. I even tried adding random noise to the data to see how it would affect it. And even with 600 spikes per pixel of random noise, it only decreased the accuracy by about 5%. And you can see in this lower plot how much noise that actually looks like. And it does make it a lot harder. And it's good to remember that, again, it's not as easy as it looks here. This data is pre-processed. It would be more spiky and sparse for the network. Now to my second task, reconstructing a normal still image from the moving and spiking image. So let's watch it train over time. These top plots are the output of the network, all this random noise looking stuff. And these bottom plots are the actual image that was moved in front of the silicon retina to produce the data. So before training, it knows nothing. It's just producing pretty much random noise, which is to be expected. And after a bit more, it sort of gets the idea that digits aren't drawn all over the place and reduces the amount it puts out. After even more training, we start to see actual recognizable figures here, still very noisy. And at the end of training, we have very clear figures that look just like the actual image that produced them. And again, we're not feeding the network these images. That would be too easy. We're giving it the silicon retina data, which is much more hard to understand. So it actually has to stabilize and integrate and do a little bit of inference to produce these results. And it's not just producing the same 9 whenever it sees a 9. It's actually faithful to the specific handwriting style and features of that 9. Loop size, tail slant, things like that. So it's actually generalizing here. So that was a success, but here's something even more impressive. Just for fun, I decided to run this network on another data set I had, which was not just handwritten digits, but all sorts of other images like motorcycles or Snoopy. So amazingly, it could sort of reconstruct these. So on the right, we have a motorcycle-looking thing and a Snoopy-looking thing. And this means it can generalize to a completely different domain of data. And it was only trained on 34 by 34 pixel handwritten digits, but it was able to work on real images of varying size that were much bigger and more complex. That's because of the convolutional architecture. It can be applied to input of any shape or size. So why is it actually inverted, you ask? Over here, we actually have a black motorcycle on a white background, but it produces a white motorcycle on a black background. And it's almost like it's drawing it because it only draws the edges. Now, this is actually a really cool way of displaying how it's applying its limited knowledge, which only covers handwritten digits, which were all white line drawings on black backgrounds, to other images. It only knows that any image is a white line drawing on a black background. So that's what it produces, of course. But it still sort of works. And remember, the initial intensity from a silicon retina isn't recorded. Some data is lost when it's recorded with a silicon retina. So it might not even be possible to perfectly reconstruct the background too. So, in conclusion, neuromorphic computers have great potential for extremely energy efficient, fast, and parallel computation. But we can't just program them. Silicon retinas have great potential for very high frame rate, high dynamic range video, but getting intensity data requires inference. So I killed two birds with one stone by combining them. I found a way to train neuromorphic computers for a task and applied it to processing silicon retina data with them. And surprisingly, I found it generalized to a domain of images completely outside that which it trained on. So I accomplished the two tasks I had set out to apply in SNN2. Classifying handwritten digits from a spiking, moving silicon retina data, and reconstructing a still image from a spiking, moving silicon retina data. So that's all. Any questions?
Thank you. Judges, questions?
I'm going to start off with an ignorant question, if that's okay. Can you kind of describe the flow of data through the different layers? I think I heard you mention that some of the layers aren't connected, and if I understand correctly, the flow is not necessarily unidirectional.
Right. So here, let me just pull up my architecture here. This is it's a fully convolutional network, like I mentioned, which means the data flows from the first layer to the second layer, and it flows in the same way because of the convolutional way it is. But it is unidirectional, like a typical neural network, because the spikes only go in one direction. They fire from the end of one neuron in the first layer to the second layer, and not backwards. But it is still firing all at once, which means a spike is fired from the first layer to the second layer to the third layer to the fourth layer. And while that spike is happening in the fourth layer, another spike is still happening in the first layer. So it's still, all these layers are going at once. Even though it starts all at the first layer doesn't have to finish calculating before the fourth layer is going. It's all happening at once.
Thank you for the clarification.
Very cool presentation. In the 90s, there were books like Impulse Neural Networks. The difference between pulsed and spiking neural networks. Have you come across that in the literature?
I haven't heard of that, but it sounds like a similar thing. Just like probably artificial neural networks were, already researched back in the 80s and 90s and stuff, but it didn't really work well until we had big data like now. So a spike really is just a voltage pulse like that. When it travels down the attenuation line of the synapse, it sort of disperses into, you might call it a pulse more than a spike because it gets less sharp.
So it was, back then they were doing it basically as coupled oscillator models, like a Hodgkin-Huxley instead of a Morris-Lacar. Do you make a distinction between like type 1 and type 2 neurons, and is this of one of those types?
I actually haven't heard of that oscillator thing. I'm just using what's called in the literature I've read as a simple leaky, integrate, and fire model.
Okay, very cool. And then, so that edge, when you saw the white lines around the motorcycle and Snoopy, do you think most of that was coming from the convolution of like the equivalent of a Sobel filter would give you the edge detection like that? Or which a convolution would be the equivalent? Or do you think that's coming because of your spiking neural network model?
Well, actually, I think it's coming from a step earlier than that, the silicon retina. Because, like I said, it only outputs a spike when a pixel changes, which means if you move something in front of the silicon retina, what you get is these lines automatically detecting the gradients for you. Like you can sort of see in these visualizations here, you actually automatically get the edges highlighted by the silicon retina.
Okay, so that's when you have a moving image, and a frame difference in convolution could give you that as well, right?
Exactly.
What about when you have a still image and you get lines like that, or do you get lines with a still image in your training?
Well, you can actually use a still image really with a spiking neural network. Well, you can't use it with the silicon retina because it's taking the difference, so you just get nothing out and you put nothing into the network.
Right.
There is another way of converting like a still image to spiking data by just pixel intensity and changing that to a spiking rate as input. But I just tested with silicon retina data only.
Okay. So is there some relationship with the eye saccade that's always moving back and forth that would be better?
Yeah, exactly. So in the silicon retina data I'm using, it has 3 separate motions, which are called saccades. It moves one motion up, one motion to the side or something, and one motion back. And that was intended to model the saccades of the eye. And some people think that's why our eye saccades so much, is to help do something like this, because a spiking neural network can reconstruct an image with these moving around.
And then one last question, you mentioned the speed of light versus the activation in a traditional artificial neural network. Do you still have to go over the synaptic cleft, or so you still have to do a chemical? Are you reduced to a chemical speed, or is it all electrical in the biological models, or is it using light? Yeah, go ahead.
Well, you could, in fact, use light, but really, I say that because it comes down to the speed at which an electrical pulse travels down a wire, which wouldn't actually be the speed of light. It'd be the wave speed in that medium, which is the metal.
But
that's
does
on
it
the
still have to
scale
go
of the
between
speed of light.
between the axon and the dendrite of the next neuron? Do you still have to go across a chemical speed versus electrical?
Well, in like a neuromorphic computer, it's just a straight wire with like maybe a diode, maybe a resistor to add like a weight or something like that.
Yeah,
Okay.
I think he's trying to compare it to actual biology where you have like a neuron and then the connection to another neuron, you have the synaptic cleft, and then it's like a biological molecule that is actually communicating with that one to the next one. But it sounds like it simulates more the neuron itself within the neuron, but not interneuron communication because it's so quick, like a light speed for computer. Am I understanding correctly?
Yeah,
That's
we're
exactly
basically in a neuromorphic computer. It's basically just a straight wire with maybe a resistor and a diode.
All right. Are you familiar with FPGA's field programmable gate arrays? If you do decide, if you're really interested in this and decide to continue on, they may be a good thing to look at. My understanding them is kind of off from a distance, but they include, newer versions of them have both digital and analog methods and components, and they're very interesting, and they may be very relevant to this.
No, I haven't heard of that. But thank you. Yeah, I might look into that.
So Robert, this is Dave Janicki. And I'm sort of looking at what you're doing and thinking of it as a photographer where, when I put my eye to the camera, and of course, started out old school with film and everything else, but, my attention goes to certain places, and then sometimes that pops up later. And it's something like the problems we all have with the CAPTCHA, are you not a robot sort of question on the net, where we can't always find the right thing because we aren't focusing in the right place. And so can you give me a little background on where these techniques developed and where they've been applied and how that contrasts with what you've done in this very elegant presentation?
Yeah, so I don't know exactly when this was, when the first idea of spiking neural networks came about. Probably from some neuroscience thing. I actually based a lot of my research on a particular paper called SLAER, which stands for Spike Layer Error Reassignment. They actually developed the idea for the algorithm to backpropagate error through a spiking neural network, and simulating it too. And I used their library for that. And what they did in that paper was just the handwritten digits thing, because that had been done so much with artificial neural networks. They also applied it to not just silicon retina, but just converting it to a spiking in pixel intensity to a spiking rate. They did not, as far as I know, use the Caltech data set of like images of normal things like motorcycles, and that's new. And they didn't reconstruct images either, just classification.
Okay, it would be interesting to take, for example, your motorcycle there one step further, and you did a lot of noise stuff, but you could also take that black and white image and look at a background. Simply put a gradient in or something like that, to test it further. And as I say, it's you've very nicely presented this for us. It's just interesting to me to think about it in the context of, how do I focus on things, and how does, some of that learning not happen almost instantaneously in real time, like like the spike neural network is defined, but things occur to me along the way, right, later. So I may take several pictures and slightly change focus or something like that in terms of how my neural network is operating. So there's some interesting processes to compare to. And I very much appreciate your response to the question talking about this layer reference. You probably could have folded that into an early part of your presentation here to give us some background, and that would be just useful in setting the context in the future. Thanks.
Yeah, and there's actually something I wanted to mention with your idea of like thinking about, one part of a problem at a time and focusing on one area at a time. Is I can't really show it here because these are still images, but remember that the input to the spiking neural network is a time series, and the output actually has to be a time series too. So to get this, what I did is sum it up. And so I wondered, what would it look like if I displayed it not summed up, but over time, like it's actually output. And the thing is, what I see is it sort of draws this thing out, almost like a human would. Like you see the lines, and it starts at one end and sort of draws along the line, which is interesting. And I think that's because as the object moves in the eye of the silicon retina, the most obvious gradient is that which is perpendicular to its direction of motion. And so it draws that first because that's what it can be most certain about. And then it rotates that around.
Okay, thank you.
All right, judges, we're out of time. Thank you, Robert.
Yeah, thank you guys.
Very cool, Robert. Nice progress from last year too.